All right, picking up with part B where we left off, we were just about to talk about naming of molecular or covalent compounds. In covalent compounds, in a way, the naming of covalent compounds is quite a bit easier than the naming of ionic compounds because once you learn the tricks, because the names of covalent type compounds just explicitly give you the numbers of atoms of each element present in the compound. And so it's really just the names of the covalently bonded compounds are really just fancy ways of reading out the formula for the compound. Unfortunately, the way that they give the number of each element or number of atoms of each element in the compound is by using those Greek prefixes that we just saw for waters of hydration, rather than just using the English number. So, and the Greek prefixes would be used before the name of each element in the compound. And so, in other words, each element gets its own prefix. Another important thing to keep in mind is the element order. And this goes for both the formula and the name. In ionic compounds, it's pretty straightforward. Cation first, anion second. But in covalently bonded compounds, you don't have ions. So you don't have a cation or an anion. So it's harder to say which one should come first. The convention is that the more metallic element comes first and the less metallic element comes second. And you might say, what do you mean more metallic or less metallic? Either it's a metal or it isn't. But actually, it turns out a lot of the characteristic properties of elements can vary as to degree. So things like how hard is it? How shiny is it? How well does it conduct electricity? And things like that actually do vary within the metals and within the nonmetals. And generally the way the periodic table is laid out is the more metallic elements are to the left and to the bottom. And one of the main characteristics of metals is that they like to lose electrons in order to become cations. And so you can certainly rank the elements according to their ability or their desire to lose electrons. And it turns out that the elements that most want to lose electrons are down here in the lower left-hand corner of the periodic table. Cesium and francium have barely any hold whatsoever over their electrons. And they will practically start throwing electrons at you just if you look at them funny. Whereas the elements that have a very strong hold on their electrons and are therefore less metallic tend to be up here in the upper right-hand corner of the periodic table. So you actually can draw out a trend for metallic character among elements. Greater metallic character tends to be toward the left and down, and less metallic character tends to be to the right and up. And you can think of the two extremes. Fluorine is extremely non-metallic, and francium is extremely metallic. And those are kind of the two extremes. So if you just remember those two examples, that can help you suss out what the trend must be. Okay, so generally when we say the more metallic element comes first, what we mean is the element further to the left or further down the periodic table should come first in the formula. And then when we say less metallic element, we mean the element further to the right or closer to the top of the periodic table should normally come second. There are a few exceptions to that rule where compound formulas have been, or basically formulas for well-known compounds have been written contrary to that rule for so long, and they're so well known that way that they continue to be written that way today, even under these rules. But these would be the normal rules right here. So the name of the second element ends in IDE, as if it's an anion, but it isn't. Don't forget that, it's not. And then the name of each element gets a prefix. The prefix would be the same as the ones that we used for the waters of hydration. So just as a quick review, mono would mean 1, di would mean 2, tri would mean 3, tetra would mean 4, penta would mean 5, hexa means 6, hepta means 7, octa means 8, nona means 9, deca means 10. And you can go beyond 10, but I'm not really going to worry about that. The one exception to that rule is that mono is dropped if there's only one of the more metallic element. So in other words, the compound name will never begin with mono. And that's because as it works out, there are many, many, many millions of compounds that consist of molecules where there's one of the more metallic element and several of the other element. And if we named it strictly according to the rules, there would be literally millions of compounds whose names begin with mono. And searching through chemical dictionaries and that kind of thing would be like the M volume would be bigger than all of the others combined. And so they decided to simplify things by never using mono for the more metallic element. And the best way to learn that was probably looking at examples. There is a table on page 111 in the text that you can look at. Here are some examples. Some of these are in the table and some of them aren't. If you have a compound where the formula is CO, made up of carbon and oxygen, 2 nonmetals, it would be CO again because carbon is to the left of oxygen in the periodic table, making carbon more metallic than oxygen. And that would be called carbon monoxide. Couple things to notice here. Notice it's not monocarbon monoxide. You don't use mono for the first or more metallic element. And also, when the name of the ion begins with a vowel, you can often condense the vowels. This is not monooxide, it's monoxide. Okay. Particularly if they're like both round vowels, like, well, in this case, it would be 2 O's. You can condense those 2 O's down to 1. So instead of monooxide, it becomes monoxide. CO2 is carbon dioxide. Okay, not monocarbon dioxide, but carbon dioxide. SO2, notice with sulfur, sulfur is below oxygen, so that's the more metallic element present. Oxygen is less metallic, so sulfur comes first. That would be sulfur dioxide. Again, not monosulfur dioxide, but sulfur dioxide. SO3 would be sulfur trioxide. In compounds with nitrogen and oxygen, the nitrogen comes first because nitrogen is to the left of oxygen. So nitrogen comes first, then oxygen. And N2O, its official name would be dinitrogen monoxide. Okay, so for the first element, nitrogen, you do use a prefix because there's more than one of them. So it's dinitrogen monoxide. This compound is better known as nitrous oxide, but the official name would be dinitrogen monoxide. For NO, this would be nitrogen monoxide. Again, not mononitrogen monoxide, but nitrogen monoxide. And that's better known as nitric oxide, but still the official IUPAC name is nitrogen monoxide, and that's what we'll call it. NO2 would be nitrogen dioxide. And this is, you're seeing the reason here why we use this system for naming covalent type compounds, because when you're combining nonmetals with each other, there are often a lot of different combinations that are possible. There's N2O4, for instance, dinitrogen tetroxide. But notice when you know the meaning of the prefixes, dinitrogen tetroxide really just means 2 nitrogens and 4 oxygens. That's exactly what the formula says. So they're really just telling you exactly the same thing. It's just that part of this is in Greek. N2O5 is dinitrogen pentoxide. And so it's pentoxide rather than pentaoxide in order to make it easier to say. But if you write pentaoxide, I'm not going to count it as wrong. P4O10, tetraphosphorus decoxide. Again, technically not decaoxide, but if you write it as decaoxide, I won't count it as wrong. So tetraphosphorus decaoxide. One of the few compounds formed by any of the noble gases is XeF6, or xenon hexafluoride. There's also XeF4, which would be xenon tetrafluoride. Okay, and so you can work with all kinds of examples like that. And before we get too far, we also should mention naming of acids. Acids are compounds that are very common in chemistry, and they're used for a lot of different things. And they're used, actually, they're encountered quite commonly in daily life too. Just about anything that tastes sour is that way because of acids. Things like oranges and lemons taste sour because they contain citric acid. And vinegar and ketchup taste sour because they contain acetic acid. And some colas, dark colas like Coke and Pepsi, they have a certain sourness to the taste, which is mostly masked by sugar, but there is a certain sourness there in the background, and that's because they contain phosphoric acid. Acids are found in a lot of other things too, including things like household cleaners. Toilet bowl cleaner contains a variant on sulfuric acid, and so on. Anyway, acids are an interesting situation because acids are technically not ionic compounds, but they ionize when you put them in water. So they're not ionic, but they give off ions anyway. And so that's kind of an interesting bridge between covalent and ionic compounds. Acids involve generally H+ ions plus a negative ion. And so that's how you can tell an acid when you see it, is it will generally take the form of hydrogen followed by a negative ion. Okay. The simplest acids will be binary acids, which consist of two elements, hydrogen and a nonmetal, in the form of an anion. So H+ plus a monatomic anion, that is a nonmetal, like say HCl, HBr, and so on. The pure compounds for this type of acid are actually gases, and when they're in the pure form as gases, they are actually named as ionic compounds. Okay, even though they're technically not ionic compounds, they're named as ionic compounds. And so when you see hydrogen followed by a negative ion or a nonmetal, that would be named as an ionic compound if it's a gas. But when they're dissolved in water, they act as acids. Because, well, the basic, most fundamental definition of an acid is something that gives off H+ ions in water. If you put something in water and the number of H+ ions in the water increases, then what you put in the water was an acid. Okay, so, but notice the definition, in water. Something cannot be an acid if it's not dissolved in water. So when these compounds are pure compounds as gases and not dissolved in water, that means they're not acids. And so they're named as ionic compounds. But when those gases dissolve in water, and they actually do dissolve in water quite easily, they become acids and they're named as acids. You can tell that it's dissolved in water because the formula will be followed by a little AQ in parentheses, which means aqueous. And aqueous just means dissolved in water. And as acids, there's a different naming system. You don't just call it the name of the ionic compound. And when in water, the acid compound ionizes to form H+ ions and the anion. And those are both dissolved in water. And so the acid naming for binary acids, that is when these compounds are dissolved in water, would be the hydrogen part of the name that you would normally call it as an ionic compound becomes hydro. And the name of the second element ends in IC, ic, and then you add the word acid. And some examples follow. Okay. So for instance, the compound HF. You've got hydrogen followed by a nonmetal. So that's going to be an acid if you dissolve it in water. But if it's the pure compound, it'll be a gas and you'll name it as an ionic compound. So as a gas, or in other words, as the pure compound, you would call this hydrogen fluoride. But as an acid, if it's dissolved in water, you would take hydrogen and make it hydro, and fluoride becomes fluoric, and it's all one word actually. And then that's followed by acid. So HF as a gas is hydrogen fluoride. HF aqueous, dissolved in water, in other words, is hydrofluoric acid. HCl would be hydrogen chloride as a gas or as the pure compound. But if it's dissolved in water, it becomes an acid and you call it hydrochloric acid. Similarly with HBr and HI, you can see those examples there. H2S is another fairly common example. As a gas or as the pure compound, this would be known as hydrogen sulfide. But as an acid dissolved in water, it's hydrosulfuric acid. Hydrosulfuric acid. Okay, and so those are the binary acids. Much more common type of acid would be what are known as oxyacids. These are acids that involve H+ ions and polyatomic ions. And there are a lot more of these. And there's a much wider variety of properties too. They will ionize in water to produce H+ ions and the anion, whatever that anion is. And again, producing H+ ions in water is one of the definitions of an acid. We'll go into acids in a lot more detail later in the chapter on acids and bases, but for right now, we'll stick to this. These compounds, the oxyacids, only exist in solution. They don't exist as pure compounds not dissolved in water. So they will always be aqueous. Yeah, they're always aqueous. So they're always named as acids. When it comes to naming the oxyacids, you leave out the word hydrogen. The name is based entirely on the name of the polyatomic anion. If the anion's name ends in ATE, then you replace that with ic and then add the word acid. If the anion's name ends in ITE, then you replace that with OUS or US and tack on the word acid. And so you basically name it according to what polyatomic ion it contains. So HNO3, when you see hydrogen followed by the nitrate ion, this is, again, an oxyacid. It exists only in an aqueous form dissolved in water, doesn't exist as a pure compound. So you don't call it hydrogen nitrate. You would call it, since it involves the nitrate ion, the 8 becomes ic, and this is nitric acid. If you have HNO2, you may notice NO2, hopefully, as the nitrite ion. And so ITE becomes OUS, and we would call this nitrous acid. H2SO4 contains the sulfate ion, the SO4 part, and that would be called sulfuric acid. And you can use these rules in reverse if you're given the name of the acid and you want the formula. Sulfuric acid, you would know, since it's sulfuric, that would mean that it must contain sulfate ions. The sulfate ion has a formula of SO4 minus 2, and that means it takes two H pluses to balance the minus 2 charge on the sulfate ion, and so the formula must be H2SO4. H2SO3 includes the sulfite ion, and so this would be sulfurous acid. And then we get to the chloride oxyanions. HClO4 involves perchlorate, so that's perchloric acid. And similarly with HClO3, HClO2 involves the chlorite ion, so that would be chlorous acid. HClO involves hypochlorite, so that would be hypochlorous acid. HC2H3O2 includes the acetate ion, and so that's acetic acid. H3PO4 includes the phosphate anion, and so that would be phosphoric acid. There's a certain amount of memorization involved here because, of course, sometimes you drop more of the element's name than you do in other cases, or drop more of the ion's name than in other cases. Like sulfate, going strictly by the rules, you would expect an acid that contains sulfate ions to be called sulfic acid, but it's actually sulfuric acid. And this is H2SO3 is not sulfus acids, it's sulfurous acid. And phosphate, you would expect that to be called phosphic acid, but it's actually phosphoric acid. So even if you go by the rules, there's still a little bit of memorization that's needed. All right, well, finally, that brings us to the end of chapter 2. The chapter 2 homework questions, those will be due next Tuesday. And it's about the time in the semester we should be thinking about having our first exam also. So that will be coming soon. I'll let you know on that. And that would cover chapters 1 and 2. Okay, so that's the end of chapter 2. And in the next segment, we will begin chapter 3. See you in a minute.